All right, so let's jump into things here today. So we did frequency distributions and a lot of Excel work last class. So today we're going to kind of transition away from that. Right? So we've got terminology I brought up last week was descriptive statistics. So these were basically different statistics we can calculate that tell us something about the data. Right? So how can we do this for populations and samples? The first one we're going to be focusing on are measures of central tendency. Right? So anytime I have like any distribution, right, I might want to know like kind of where the middle point of that distribution is. Right? Now visually, like on this one, it's probably like somewhere around here. But you know, how can I actually calculate that, and how can I get a value to represent that? So we've got three different measures. We'll talk about all of them today. I'm going to start using some more notation. So anytime we're doing something for a population data set, we typically notate that with a Greek letter. So notice for the mean, we're going to use mu. Right? So here's our mu, here's population mean. For our sample mean, we're going to use kind of our more like the English alphabet usually. So X bar, X with a bar over it, that represents, we found the mean from sample data. We then have the median and the mode. Those ones are going to be two pretty easy ones. We're just going to capital M subscript E, capital M subscript O to represent the population, median, and mode. I don't have it up in the slides because it really doesn't impact anything we do and doesn't really matter. It doesn't change a whole lot. But if you wanted to write this for a sample, it's just lowercase m D or subscript D, lowercase m subscript O. But that's not ever going to really play a role in anything we do. So here's our three measures of central tendency. We also have measures of dispersion or variation. So the variance and the standard deviation. So population variance, sigma squared, right? We use that Greek lettering. The sample variance, right? Calculating the variance from sample data, S squared. Going back to using our kind of English alphabet. And the standard deviation is just us scaling the variance. So notice, you know, sigma and S represent the population and sample standard deviation. Well, to go from the standard deviation to the variance, all I'm going to do is square the standard deviation. Right? So they're kind of just like a scaled version of each other. And we'll talk about why we need, or why we might be interested in both of them later on. Any questions on any of the notation or anything at this point? Yeah. So how do you calculate a mean? So if I'm going to calculate a mean, I've got the everything written out here. But if I had 5 numbers, how would you find the mean, or how would you find the average? Yeah. Anyway. Yeah, you just add the numbers up and you divide by 5, or you divide by the number of numbers you added up. Okay? So if we're going to find the mean for this huge data set, what we're going to do is go through every observation, add up the value for that X variable for every observation, and then divide by, well, how many numbers would we have? The total number of observations. Right? So we're going to go to the very first observation, take the value we see for the X variable, add to that the second observation's value for that X variable, add to that the third, all the way up to the last observation, which we're going to call capital N, the total number of observations in a population data. So X subscript is N, that's then go to the very last observation. Add up all the values, and then divide by, well, how many observations will we have? Well, whatever the number is in our population data set, so divide by capital N. That's how we'll represent this kind of notation. But yeah, it's just a complicated way of saying exactly what you told me. Add the numbers up and then divide by the number of numbers you have. Now, another way of writing this, I just introduced this here because we'll use it a little bit later on in the semester, but this capital sigma, this summation sign, I don't know how many of you are familiar with this or have seen this before, but it basically means start with the first observation and then add up everything that's on the right-hand side of this summation sign, which is just the variable X. So start with the first observation, take its value for X, add to that the second observation's value all the way up to capital N of the last observation, which is basically what I have written here as well. There's 2 different ways of showing the same thing. Okay? So what if I want to calculate a sample mean? It's the exact same thing, exact same process, just a little bit different notation. Now, from sample data, it's X bar instead of mu. I'm going to start at the first observation and go to the last observation of my data set, which is no longer capital N, but now the number of observations in my sample is that lowercase n. Okay? But procedurally, once I actually have the numbers, it looks no different, right? Any questions? Okay, any questions on this before we keep moving? All right. So let's say I had this data set where I had every birth in the United States and what different variables, right? And one of the variables was birth weight. How would I find the average birth weight in the US? I take up every single birth, add up all the weights, divide by the total number of births I had in that data set, right? And I'll get my answer, which is not near as heavy as I would have thought. But maybe that's because people want to talk about babies that weigh a lot. So I don't know. But pretty easy, probably a review for a lot of you. We'll call it mean in this class. A lot of times when other classes maybe reference something like this as the average. Same idea. It's just the technical term that we're going to try to use is mean here. So if we had an example like this, also I was going to use iClickers today, and something's wrong with the way I have it set up, so it's only working for Reef people and not anyone else. So I'll be troubleshooting that this afternoon and tomorrow. That hopefully we'll be starting using those on Wednesday. Okay? And I'll have a couple in here that we'll kind of look at. Also, I know there's like some backwards on some of them, so that way we kind of avoid that. So let's say I had a data set like this, some game, I don't know, it could be basketball, it could be Bible, and I want to find the population mean. Right? Well, I've got 7 different games. So what am I going to do here? I'm just going to go through, add up the points scored from every single game. So 20 plus 35 plus 15 plus 18 plus 28 plus 35 plus 16. Whatever I get there, I'm then going to divide by the number of observations I have, which here it's pretty easy to see. I've got 7 observations. Right? So it's that easy to calculate the mean. This should be kind of review, shouldn't be anything too tough probably for you guys. So usually I would do like an IQ question here, where I show you a very similar data set, right? 7 observations, but it's a different variable. It's now commute time from some company called ECON. What would I do here? Add up all the commute times, divide by the total number of observations, which would be 7. I usually show you some answers like this, and then I show, let you respond, and then I show you how you would actually calculate it. Ends up being 45. Okay. Went through that pretty quick, but I don't think we probably need to spend a lot of time on that. So what about the median and the mode, right? So the mode is going to be the outcome that occurs most often, right? So if I think about what we were doing before, when we had histograms or frequency distributions, if I had a more continuous distribution with a lot more bars, how could I identify the mode pretty quickly? Remember, what were those bars we were using? We used frequencies. Yeah, just whatever the highest bar is, right? Because remember, what was on the y-axis here was frequencies for all these different responses. So the response that was the most often occurring would be the one that has the highest frequency or the highest bar. Right? So that's all the mode is. You go through, and I had someone in another section ask this question earlier. I think I have a good way of explaining it. So when we talk about data sets, we've got observations, right? I might have, maybe I'm recording height, right? And I've got 1,000 different people, 1,000 different observations in my data set. I've recorded 1,000 different people's height. However, the response of 72 inches, I could see multiple people have the same response for that variable, right? So we've got multiple observations, and what we were graphing was how frequently we saw different responses, right? Because multiple observations could have the same response. So the mode's not too bad. The median is going to be the value that if I were to arrange the data from smallest to largest, it would exactly have, it would have 50% of the observations to the left and 50% of the observations to the right. Okay. So easy way to think about this is if I have, let's say I had 3 numbers, I'll make it real easy. I arrange them from smallest to largest. The median value, I cross out the highest, cross out the lowest. The value that's exactly in the middle of this data set would be 4. Right? What if I had a slightly larger data set? Cross out the highest, lowest, next highest, next lowest. The value I'm left with in the middle, that's my median. Okay? There's 50% of the observations above it, 50% below it. Now, what happens if I had something like this? Cross up the highest, cross up the lowest. If I cross up the next highest and the next lowest, I'm not left with anything. So if I have an even number data set, I'm going to be left with two numbers in the middle, and I'm simply going to find the mean of those two numbers. All right, so there's like one more step, but pretty easy. So here, I'd add them up, divide by 2, and the median would be the mean of these two numbers, which is 5. Or the average of those two numbers. So if it's odd, right, it's pretty easy. It's just going to be that value that's left in the middle. If it's even, we'll have 2 left in the middle. We'll take the average of the 2. Let's kind of look at some actual examples of this. Makes it a little bit easier, I think. So let's say I had the point score data set. I would go through, cross off the highest value, cross off the lowest value, cross off the next highest, cross off the next lowest, cross off the next highest, cross off the next lowest. I have crossed all these out. I'm left with just that value of 20. Now, this question didn't say median, it says mode. So I'm actually going to wait. But that's how I would find the median. How would I find the mode here? Yeah.
You look to see which number first and then.
Yeah, so what's the only number that even happens more than once here? Yeah, so my mode would be 35, right? It's the one that happens the most frequently. It's a response I see the most often. And then the median we kind of talked about. I go through, cross off the highest and the lowest, next highest, next lowest, next highest, next lowest. And I'm left with that number. And it's easy because it's an odd number data set. Any questions on any of this? That's easy to make mistakes if I have a bigger data set and I'm doing this by hand. I'll do it this way. So let's say I use that commute time data set. And maybe I give you some possible responses. And I look here, it's probably a little bit easier if I arrange them from smallest to largest. Well, we might play around in Excel a little bit today, and I'll show you an easy way to do this with data. But once I've arranged them, now it's really easy to just go highest, lowest, right? It's a little bit easier to make sure I don't like overlook a value, right, when looking at the data set. So that's another way we can kind of find the median for doing this by hand. So one thing I want to point out about the mean and the median, let's say in this example, one of the possible responses, let's say instead of 35, it said 15. Why could you rule out 15 right away? What? We got not 15 would be the lowest, right? But it's because it's below the lowest value, right? We have to remember, if we're looking for means and medians and modes, they have to be somewhere. I mean, they are in the middle, but they at the very least have to be somewhere in between the minimum and the maximum value. So anytime you see an answer that would be outside the minimum and maximum value, you know those are just ridiculous answers. You can cross those out right away, right? Remember, this is where we don't get too lost in what we're doing here. Like, because I could very well, if I'm finding the mean, I could very well like make a mistake and forget one of these numbers or accidentally add a 0. If I get something that's outside the range of the possible, like the minimum and the maximum values, I know it's something wrong, right? So let's remember, we're trying to find like the middle point of this data. Okay? Even here, if I'm looking and I see something like 80 doesn't, I just look at the data, I'm like, well, most of the data is at the very bottom. I don't think the middle of this data set is going to be 80. That seems a little weird, right? You start to kind of critically think through the possible answers. All right, so the median mode. Oh, I want to touch on something we talked about last class. I'll give you an example first. So we talked about skewed distributions, right? Let's think about, let's say I've got something like this. Start out with this example. So 2, 4, 6, 8, and 10 is my data set. If I wanted to find the mean here, it's what? 10, 10, 10. So 30 divided by the number of observations I have. So 5. So 30 over 5, 6. I wanted to find the median. Cross out the highest, lowest, next highest, next lowest. Median is also 6. Right? This kind of lines up with a normal distribution because our data, right, is a small data set, so I can make sure it was like this, but our data is symmetric, right? From the middle point of the data, it kind of falls off equally as I move in either direction. So when we have a normal distribution, the mean actually ends up being the same as the median. Now let's think about if I had a data set. Look like that. almost the same data set. It's just that the highest value now is an extremely large value, kind of like an outlier, we usually call it. Okay. So now if I look up the mean, it's going to be 120 over 5. So what, 24? I'm doing math in my head correctly. And then the median, though, is still just going to be 6. So notice the median was not influenced at all, or is influenced less by extremely large values, right? Or extremely small values if we want on the other end. However, the mean can be greatly influenced, especially in a small data set, by these really extreme values. So if we have like smaller data sets, sometimes the measure of central tendency we probably want to rely on more is the median, because I mean, the majority, 80% of this data set is in between 2 and 8, right? And so the median is probably a little bit more better reflection of the middle point of that data set when it's really small. Now, as we get larger data sets, there won't be as much of a discrepancy from an outlier between our median and our mode, because it's just 1 out of a million observations instead of 1 out of 5. But, you know, we can start to think about if we did have an extremely large value, what that's going to do is it's going to pull the mean up, right? If I'm thinking about the average income, when Jeff Bezos gets added in there, he's going to pull the average up a lot, right? So if we have this, you know, these extremely high values, that's going to be represented by a long right tail, right? There's some really high values, not a lot of them, but there's some of them out there. So it's going to pull the mean to the right and not impact the median near as much. So anytime the mean is to the right of or greater than the median, we have that right skew distribution. I said visually it's easy to think about because it's got a long right tail. But having that long right tail, if I gave you the mean and the median of any data set, you can tell me which way the distribution is skewed. If the mean is to the right of the median, it's right skewed, right? It's got some really, really high values. If we have a less skewed distribution, these really, really low values will pull the mean down, but not impact the median near as much, right? So if the mean is to the left of the median, we would say we have a left skewed distribution. So the way that those are actually named is not by the tail, but the relationship of the mean to the median. Any questions on that? Does that make sense? All right, so kind of comparing some stuff we talked about last class. Where are we at with time? This one's pretty easy. I'm sure you've used this in terminology, but all right. The very first measure of dispersion we're going to look at, or the measure of variation, is going to be the range. So the range of a data set is just the difference between the minimum and the maximum, right? What's the difference between that smallest and largest value? So here we can kind of see this commuting time data set. The maximum is 90, the minimum is 20. So our range would just be the difference between the two, or 70. And you got to think about a measure of variation. It tells us something, right? Because what would my range be for this data set? Largest value is 100, smallest value is 2, so the range would be 98. What's the range for this data set? So it tells me, right, a range of 8, there's much less variation, right? This one, there's a lot more variation because of that one extremely large value. Now, the problem with the ranges, I have to make sure, I don't think I have any examples that we worked through this. No, we're going to write the variance. The problem with the range is, like, what if I had a data set that looked like this? And it had 100 or it went from 1 all the way up to 100, right? I had exactly 1 observation on each value. But then I have a data set that looks like this. All 1s, but then it's 100. What's the range of both these data sets? 99. But there's a lot more variation in this data than there is in that one, right? So the range is a good starting point, but it doesn't really tell us much about, you know, we could have data sets with the same range that have a much different variation. So we're then going to move to a better measure of dispersion, which is the variance. Okay? So we'll walk through this formula in a second, but basically what the variance is going to capture is how much the data set varies from its middle point, right? How much the data set as a whole varies from that middle point. So I've got my population variance equation up here. So this summation sign says start at the first observation, do whatever is to the right of this sign, add to that the second observation, plug that value into this, add to that the third, all the way to the last one, and then divide by the total number of observations. So if you think about what's in that numerator, it says, okay, take the value of X for that very first observation and subtract the mean. So we're going to look at, eventually, every observation's deviation from the mean. So that difference there, we'll call that the deviation of that observation from the mean. So how far away from that middle point of the data set is that one observation? We'll then square that value, right? So what squaring that value does is two things, right? The first thing is, let's say my mean was 50. If I see a value of 40, that's 10 below. If I see a value of 60, that's 10 above. 40 and 60 are the same distance away from that value of 50. They're the same distance away from the middle point of that data. But if I just keep the negative and positive signs, when I add them all up, they just cancel. So by squaring it, a negative times a negative is a positive, and a positive times a positive is like, so being 10 away in either direction counts against the variance the exact same amount. What it also does is, if you think about, let's say I saw a deviation of 1. I was 1 away from the mean. When I square that, what do I get? If I'm 2 away, when I square that, I get 3 away, square that, I get 9. As I get further from that middle point, notice when I'm squaring the value, it over penalizes these like being really far from the mean, right? So the further I get away from the mean, by squaring it, I'm like over penalizing kind of those observations. Okay. Oh, over penalize the word, but I'm using it. So any questions on it? So that's kind of the notation, kind of the logic behind what we're doing. And then kind of dividing by the total number of observations. I'll give you a little bit of insight into that, and it kind of applies to the mean as well. So first I'll do it for the mean, and then we'll kind of think about the variance. When I was doing the mean, I said one way of thinking about this, I don't know, let's just say we have 3 numbers to make it easy. Or 4 numbers, sorry. So I would be dividing by 4. Another way of writing this is like this. So notice, really what I'm doing when I divide by the total number of observations, it's like the weight of each one of these values is 1 out of however many I have. So each one, x1, x2, x3, x4, they're all being weighted by 1/4 because they're 1 out of 4 observations. Well, if instead I had n number of observations, it's just going to look something like this, where every observation is weighted by 1 out of however many observations I have. And that's really what's kind of happening here. Every deviation from the mean, every observation's deviation from the mean, by dividing by n, it's really like we're weighting each one by 1 over total number of observations. Sample variance, the exact same thing. We have a little bit of difference in notation. Instead of the population mean, we're looking at the deviation from the sample mean because we're dealing with sample data now. However, if we only have sample data and we are calculating a variance, instead of dividing by the total number of observations, we divide by n-1. So a little bit, without going too deep in detail as to why, we need to do this when we get to things like confidence intervals and hypothesis testing, because the size of our sample will automatically bias our variance calculation, even if we were able to look at the true population data. So the idea here is, if we divide by n-1, so we always know that if we have sample data, we're not capturing every single observation. So as we have more observations, there's just going to be more variation. And so if I divide by n-1, if I divide by 50 instead of, sorry, maybe easier. If I decide to divide by 3 instead of 4, right? Dividing by a smaller number is going to do what to that sample variance? If I divide by a smaller number, it increases the there. So If I divide by 3 instead of 4, it's going to make the sample variance higher than if I just divided by n. So I'm always kind of like erring on the side of caution. I'm always making the variance a little bit higher because I know I've only got a sample and the population data likely has a little more variation, right? Like I said, once we get to some hypothesis testing stuff, we'll start to think about things like degrees of freedom, and that'll apply to that as well, because we'll be using a sample variance, so we need to evaluate n-1. But that discussion is for later on. For now, just know that if we only have sample data, you have to calculate the variance a little bit differently, which is it's the same process. It's just instead of dividing by n, you divide by n-1. And we probably will have to do that most often because we do deal with sample data more often than not. The units of the variance is just going to be whatever the measurement of the variable itself is. So that's pretty easy. I want to think about breaking the steps down, maybe to make it a little bit easier. So the first thing I'll do is I need the mean. I'm going to find every observation's deviation from the mean. The first thing I need is the mean, right? And you can find the sample mean if we had sample data. Then for every observation, go through, subtract the mean from that observation's value for the x variable you're interested in calculating the variance for. Take each one of those deviations from the mean, square them. Write those numbers down, add up all those square deviations, and then divide by n if it's a population data set, and -1 if it's sample data. Okay. We'll walk through some examples here in a second. What do I want to do here? I wanted to do. I'll walk through it. Let's say 2, 4, 6, 8, 10. If I wanted to find the variance for this data set, remember, I think before we said the mean was what? 6. Okay. So I'm going to go through and find the deviation from that mean for each one. So here I'm going to take, I'm going to write this over here more, sorry. So we've got the mean up here at 6. So 2 minus 6, -4, 4 minus 6, -2, 6 minus 6 is 0, 8 minus 6 is 2, 10 minus 6 is 4. Notice values that are the same distance from the mean, right? 2 is 4 below, 10 is 4 above, have kind of varying signs. So the next thing that we had to do was, we should actually be, and we don't have to do this in parts, we could do this all at once. It's a little bit easier to see if I break it up in parts. Take that deviation and square it, right? So 16, 4, 0, 4, 16. Now notice values that were the same distance away from the mean are going to add the same value to that variance, right? Because they represent the same amount of variation in the data set. They're both equally as far from that middle point. Also notice, if you had a value that was equal to the mean, that actually is a symbol of no variation in the data set, right? That one observation was evidence that there was no variation, right? So it added nothing to the variance. However, values that were further from the mean added much higher amounts to that variance because they were observations that represented that there was more variation in the data set. Okay? So then the last step is add all these up. So I get what? 40. If this is population data, we divide by the number of numbers we have or the number of observations. With sample data, we would have divided by not 5, but 4, n-1. Okay. Does that kind of make sense? So you can break it up into parts. If you want to, like you can skip this and do all this at once and write the numbers down. You can enter it all up one line in your calculator. It's just, if I break it down, it makes it a little bit easier to not make a mistake with parentheses or things like that sometimes. At this point, let's say instead, so that would have given us that original data set at 40 over 5. So we had a variance of 8, right? Let's say instead I change that data set to the last observation is 100. All right. Actually, the whole thing's going to change now because this new mean. I believe when I calculated it earlier, it was 24. So now I have to go through and find the deviation of each one of these from the mean of 24. And you kind of can imagine, like, all of these are going to be further from 24 than any of our old observations were from the mean. So this variance is going to end up being much, much higher. And honestly, it was just from one observation was different, right? So the variance is going to really capture, unlike the range, right? It's really going to capture the variation that we see in the data set a little bit better. Okay. Another question I wanted to ask here was, thinking about the earlier one where I had one of the observations was equal to the mean. What's the lowest my variance could ever get? Zero, right? Because the lowest value any observation could add is zero, right? As soon as it deviates from the mean at all, because I'm squaring it, it adds some positive value to that numerator, right? So the only time I get the lowest value I can add is zero. So if I had a variance of zero, what would that data set look like? You would just have to have the same number as every observation, right? That way, no observation had any deviation from the mean. So you're always adding in zeros there, and you're going to have a variance of zero. Not very likely, not a very interesting example. Why? I mean, that's all the same number, right? So that does help us think about it is the variance should always be positive, right? Our variance is always going to be a positive value. And we then going to move from the variance to the standard deviation, right? It's going to be the exact same process, but all we're doing is taking that variance and taking the square root of it. So the variance is 100, our standard deviation is 10. So this might seem really dumb, like, okay, now we're just like transforming, our statistics, we're just scaling them. But the reason why we do this is because once we get to confidence intervals and hypothesis testing, we're always going to be dealing with the standard deviation. It's just that the variance is going to be kind of how, we use the variance in certain situations, standard deviation in others, just to make different formulas easier. Okay. I already kind of mentioned the notation we use, sigma and s. And that should kind of help you remember, like, this is just the square root of the variance, right? If I had sigma squared, when I take the square root of a square, it cancels, because technically, taking the square root is actually like taking something to the 1/2 power, and so we end up with just sigma when we take the square root there. Any questions on this? We keep moving. Shouldn't be too bad. All right. Do I want to jump into this? Yeah, probably got enough time. So this is like an old one now. It's like 20. I don't know. I found some old star thing that had this out there, but it was in a nice, easy to grab data, so I'm using it. So I also think it's a good example of like if we had company data, what it would look like. So I've got from some year all the salaries of people that work with the football team here at Ball State. It kind of mimics. I liked it because I thought it mimicked the company. Like, here's my CEO. Here's like my employees moving down to like maybe my janitor or something like that at the bottom. All right, so it's pretty reflective of what I might see at a company. Obviously, like not everyone here is earning the same salary. Looks like a lot of them are kind of centered there, like around 80 to 100,000. But I've got some outliers kind of on either end here as well. Okay. So what I could go through and do is what will be the population mean salary, right? Well, all I'm going to go do is go through the data set, add up every salary, and then divide by the number of coaches I have in this data set. Right? So that's easy enough, right? Add all those up. I've got 10 coaches in that data set. I get about 134,000. Now, the interesting thing about this mean is if I go back, only 2 people are making more than that. The other 8 people are making less. So if I think about what the median is going to be the number that's smack dab in the middle. My median is going to be what? These are the 2 middle values, so the average of those 2. So my mean is way higher than my median, or I have a right skew distribution. It's to the right of my median, so it's a right skew distribution. I could then use that mean to calculate the variance. Right? If I want to calculate the variance, what I'm going to do is go through every observation. I'll show you easier. Take the very first salary, subtract the mean, square it, add to that the next observation's deviation from the mean, squared. Add to that the next observation's deviation, so on and so forth, all the way to the very last observation. Then I should be dividing by the total number of observations, right? So it should divide by 10. Another way of writing that mathematically, and I'll sometimes do this just to save room and the way I present on the screen, instead of dividing by 10, I could also multiply by 1/10. It's the same thing mathematically. So whatever way is easiest for you to think about, it's just kind of hard when I'm typing it on the slides. If I put a big line here and it just it doesn't look kind of goofy, and it's a little bit easier to kind of display it this way. And you might see it shown that way in the book or different places. So I know, go ahead, do this on my calculator, it'll be about 14,000. So that's going to be my measure of the variance. Now, what does this tell me? It's a little bit hard to think about what the variance is really reflecting to us unless we're comparing across data sets, right? So I can compare this variance to like other team salary variances and say, if they have a higher variance, there's more variation in their employee salaries. But in terms of like what it's really telling me, it's hard to like put a real good interpretation on that, right? I mean, I know the closer to zero it gets, the less variation there is, and the higher it gets, the more variation, but this specific number doesn't tell me a whole lot. I won't really be able to get great interpretations in terms of comparing across different variables until we would get to something like probably, maybe before confidence intervals. When we start talking more about the normal distribution, which will be right after the first exam, we'll have a little better idea of how we can use the standard deviation to think about the variation. But for now, we just want to be able to kind of calculate it, right? So I think someone asked me what I said in class. The first third of this class is a lot more computation. The next third, a little more interpretation and thinking about how we kind of use what we're calculating. And then the third is there's a lot of interpretation. We're kind of black boxing, having computers do the computation for us and really using what is spinning on us. So if I have all these salaries, go ahead. What I could also do is, I think this is an easy way to do it by hand. Calculate the deviation squared, write them all down. Because in a calculator, I have to use a lot of parentheses. It's going to be this long line. I could very easily make a mistake. If I just got a small data set and I go through and calculate it for each observation, like the deviation squared, then add them all up, it's a little bit less likely I make a big mistake. Okay? So I add all these up, and then last thing I have to do, divide by the total number of observations, and hopefully I get that same value I did before of 14,000, right? So just breaking it up into parts, I think sometimes helps. Okay. Questions on this? Shouldn't be too bad. Sample variance is going to be the exact same thing. So we divide by n-1. So I'm going to show you something. And you don't have to worry about reproducing. I'm just showing it to you. It's kind of interesting. I'm not going to make you reproduce this. But there's actually another equation that we can use to calculate the variance. It's just not as intuitive. Like the variance, this is like the correct way to think about the variance, because the variance really is capturing how much does the data vary from that middle point, and seeing the deviations and squaring so that in either direction it's treated the same, and it's over penalizing extreme observations, and each one's being weighted equally, like 1 over n or 1 over n-1. That's the way to think about the variance. You can rearrange that equation and get this. This does not, is not interpretable to any of those things, right? It will work, it will produce the same value. It's just, it doesn't really reflect what the variance is actually trying to capture if you're just looking at the mathematical formula, right? But it will produce the same answer. I'll kind of walk through an example and show you why. So, we can imagine, we can probably pretty easily do these things, right? Once I calculate the mean, I can square that value, multiply the total observation in my sample. I can go through, take each observation, square its value, and then add them all up. And I could do this pretty easily, especially in Excel. I'm setting up columns. But what's interesting is it produces the exact same thing. We can do the same thing with the population variance as well. So let's say I start out with my original variance equation. And then just kind of FOIL out the top part, right? Xi times Xi is X squared, Xi times X bar is, I have a negative sign in there. So let's go ahead and I do that. Parentheses, what's in the parentheses squared? I write that out. Well, one nice thing about our summation sign is if I'm adding and subtracting, I can actually like distribute this, right? So I can put a summation sign, whoops, in front of every single thing that I have up there. And looks like I left off, this should be X bar, so I must have copied and pasted something else. But yeah, I got it back there. Okay. So then go from this line to this line. This is the part that I think is kind of cool. I mean, I guess it's a very, that word is subject to the individual. But if I then, in front of these two, multiply by n over n. Multiplying by n over n doesn't change anything because it's really I'm just multiplying by 1. Okay? So it hasn't changed anything yet. Then down here, if I have a constant, right? So when I use these summation signs, and this will come into play a little bit more throughout the semester, if I say like add up from 1 to n, or actually let's do 1 to 100, add up the value of 10. So 10 plus 10 plus 10 plus 10 100 times will just be 10 times 100, right? I would just take the number of observations and multiply it by, we call this constant C, whatever that constant is. Well, X bar squared, like that's just going to be a number, right? It is whatever the mean squared is. So if I add it to itself n times, I'm just going to get n times whatever that value is. Here's the kind of interesting thing. So the next step, we just rearrange. I can pull the constant of n out to the front, but leave the denominator n in there. And then I've got another constant, X bar, so I can pull that constant out to the front as well. And now notice all I have, and I can pull out the denominator constant. Now notice I've got the sum of X over n. That represents what? Add up all the observations for X, divide by the number of observations I had. That's just the mean, right? So this guy here is just X bar. So these just become n times X bar, or n times X bar squared. That's what we had out here. Two of these will cancel. Now I just got this equation. And we kind of pulled it out, so we don't have to worry about it. That n minus 1, we're going to have to put that back into the bottom. And so that's why that equation here will give me the exact same thing as the equation up here. Okay? I don't know. I used to geek out. I took like a real analysis class in college, and like math proofs are kind of cool because they make no sense to me. Like I could never come up with any of them. I can understand them, but I can never come up with any of them. So it's kind of interesting. We won't really use this much. Like I said, I think it's just a weaker version because this really reflects what we're capturing with the variance. But we could go through for every observation, square each X value, add them all up, right? That gives us our sum of the X's squared. We can then go ahead. So we've got, here's the mean, and cut off a little bit. We could take the mean squared. Now we've got the sum of the X's squared right here. We know n is 10. The mean squared, we calculate it here, plug it in. Final thing we have to do, divide by n minus 1 if it's a sample, or n if it's a population. And we get the exact same thing that we did before, right? So two different ways of doing the same thing. I would say if I'm doing it by hand, I'm probably doing it, this way. Like that's probably the easiest way to do it. Once we get to Excel, we'll see that these formulas are kind of useless to us. There's much easier ways to get around them. But yeah, two different ways of doing the same thing. It's how we're capturing the variation in the data set. So where are we at with time? I think we're getting close to the end. Okay, so I think hopefully we'll be able to use iClickers on Wednesday so I can iron out all the kinks. So we'll save these, we'll revisit the variance. I'll probably revisit how we calculate it. And then I'll have you kind of answer some of these questions and we'll kind of go through this. Since we got a couple minutes, I want to show you some things that'll just take real small amount of time in Excel. You don't necessarily have to follow along. It'd probably be just as easy. You could write out what I'm saying, or honestly, you might be able to remember it. So I've got this, I put it up on Canvas, it's called grade data. So it's just got a bunch of students and what it's not really their letter grade here. This ended up being their score in the course. So I think one function we talked about last week was count. This just counts the number of observations. So I'm going to use this count function, Control Shift or Command Shift on a Mac, hit the down arrow, hit enter. So I've got 431 students or 431 different grades in my stats courses. I might want to find the mean, the median, and the mode, but I sure as hell don't want to do this by hand. All right. So I'll put an equal sign. If you want to do, I hate Excel for this because I just told you earlier we should, if I didn't say it, I should have. We're calling it the mean, not the average, even though those are kind of interchangeable terms. So of course, Excel calls the mean, the function's name is average, right? So if you want to find the mean, Excel refers to the mean as the average. We'll select that first observation, Control Shift or Command Shift on the Mac, hit the down arrow, hit enter to kind of end that formula. If we want to find the median, take a wild guess at what that function is going to be called. Equal sign median, right? So equal sign median, I just select the range of data, Control Shift or Command Shift on the Mac, hit enter, and now I've got the median. That would have been a pain for me to do by hand, right? With 431 observations. And then of course, I don't want to have to count up. I could do, a little frequency distribution like I did before. That would help me find the mode, or I can use the mode function. Select that variable. Now I've got my mean, median, and my mode right there in front of me. Okay. So not too bad. We could also find the variance. So equals var.s gives me the sample variance. P gives me the population variance. And same kind of idea. I just select the number. So if I treated this as though population, it's a population data set, since it's every student I've had in my stats courses, I select that, I get my variance. And one more before we leave. STDEV.P gives me the population standard deviation. If I use .S, that would be the standard, or that would be the sample standard deviation. And I am an idiot. Hold on. I'm talking and trying to do things. So here's my standard deviation. STDEV.P gives me my population standard deviation. So I'm just going to select that. Okay. And if it was a sample, I would have just used .S. And it basically does that formula behind the scenes. It goes through every observation. It subtracts the mean, squares it, adds them all up, and then divides by a number it's stored in there also. It uses the count function and stores the number of observations. So it does all that work behind the scenes for us, and then just spits out at us what the formula would give us. So it's a lot easier, right? It saves us a lot of time. I could create columns here and do the deviation from the mean, and then another column where I square that, and I could do it all by hand, but this built-in formula for the var.p is really helpful. Okay. To end the class, what's one other way I could have found the standard deviation here if I'd already had the variance? We said the standard deviation is just the what? Square root. So the way we take a square root in Excel, SQRT, select what I want to take the square root of. Hopefully I get the same thing as the built-in standard deviation function. Sure enough, I do. Okay. So that's just a quick, I want to get that out of the way. That's not terribly tough, We'll start off next class talking about the variance a little bit more, and then kind of move into some weighted mean, weighted variance stuff. I will hopefully be using iClickers on Wednesday. I'll have everything kind of working. Other than that, your individual assignments, I've gotten some emails. If I haven't responded to you, I've seen them. I have them in their own folder. I just don't have a lot of time to work on it today, so I probably won't get you anything until tomorrow. Okay. If you sent me an email, they'll probably get a data set sent to you tomorrow. Okay. All right, we'll see you guys on Wednesday.